Object classification. ECE 542, Fall 2021, Team 6, Qua Do, Duy Nguyen, Larry Turner. Our objective is large-scale object classification. We selected a subset of ImageNet as our dataset and AlexNet as a baseline model. Our focus is to simplify and improve feature extraction and to investigate the application of generative models. We would also like to improve generalization. The ILS VRC dataset is a subset of ImageNet, containing 1,000 classes and 1.3 million crowdsourced labeled images of training data. We defined a custom data loader to partition the data into training, validation, and test sets, as we did not have access to label test data. The data loader provides data in random order across each epoch, with a specified batch size, applying a series of random image transformations. No attempt was made to identify the bounds of an object in an image, or to ensure that only one type of object was present. Yet augmentation enhances diversity. AlexNet consists of feature extraction and classifier sections. Feature extraction has 5 convolutional layers, each followed by ReLU activation and max pool, and an adaptive average pool. The classifier has 3 fully connected linear layers, each hidden layer followed by ReLU activation and dropout, and the output by softmax activation. Our CNN model. Feature extraction has 3 convolutional layers, each followed by ReLU activation and max pool with an adaptive average pool. The classifier has 3 fully connected linear layers, each hidden layer followed by batch normalization, ReLU activation, and dropout, and the output reduced by resource constraints by softmax activation. We trained with a cross-entropy loss criterion and evaluated several optimizers, including stochastic gradient descent. Differences with the baseline model include significant reduction in hyperparameters for feature extraction, including the redesign and reduction by 2 convolutional layers, and the use of batch normalization and regularization, in addition to dropout, in hidden classification layers. Each epoch was trained across a training set with 100 classes and batch sizes of 100 images, presented in random order and transformation. After each epoch, validation was performed across a validation set. An epoch required 10 minutes to complete on a laptop with an NVIDIA RTX 3070 GPU, and models were trained within 8 hours. A typical learning curve has validation and training loss in black and gray, training error in blue, validation error in red, with early stopping indicated. Accuracy was difficult to practically assess for AlexNet as our baseline model trained on all the data we reserved for test, and we were unable to access 2010 labeled test data referenced in their paper. AlexNet published results include top 1 and top 5 accuracy of 62.5 and 83%. Our CNN model demonstrated top 1 and top 5 accuracy of 64.1 and 86.5%. A confusion matrix for AlexNet represents training set performance, which is about 10% higher than test set results. The confusion matrix for our CNN model indicates similar performance on a test set. A top-n probability density evaluated across each class forms a top-n distribution, with top 1, top 5, and top 10 performance indicated. We employed batch normalization and regularization, as indicated in compact weight distributions formed from connections to each neuron in each layer of the classifier. Mean and standard deviation in each layer are indicated. Bias distributions are similar. The output layer, which did not employ batch normalization or dropout, indicated significantly larger weight deviation and a uniform bias distribution. We are also interested in the application of generative models to provide feature extraction for object classification, as the latent layer of an autoencoder represents a compact feature set which, unlike the CNN models previously described, contains information sufficient to reconstruct a representation of an image and may offer advantages in generalization and transfer learning. An autoencoder model was trained so that the encoder could be used to provide feature extraction to independently train an encoder classifier model. Our autoencoder model. The encoder has 4 convolutional layers, each followed by ReLU activation and max pool, and the decoder has 4 convolutional transpose layers, each hidden layer preceded by an adaptive max pool, followed by ReLU activation, and the output by adaptive average pool. We trained with a mean squared error loss criterion and a learning rate scheduler and evaluated several optimizers, including Atom. Our encoder classifier model. Feature extraction provided by the encoder of an independently trained autoencoder. The classifier has 3 fully connected linear layers, each hidden layer followed by batch normalization, ReLU activation, and dropout, and the output by softmax activation. We trained with cross-entropy loss criterion and a learning rate scheduler and evaluated several optimizers, including stochastic gradient descent. Each epoch was trained across a training set with 20 to 100 classes and batch sizes of 100 images, presented in random order and transformation. After each epoch, validation was performed across a validation set. An autoencoder epoch required 3 hours to complete on a laptop with an AMD 5900HX CPU Models were trained within 12 hours, as model requirements exceeded available GPU memory. An autoencoder classifier epoch required 4 minutes to complete on a laptop with an NVIDIA RTX 3070 GPU, and models were trained within 2 hours. A typical learning curve has validation and training loss in black and gray, training error in blue, validation error in red, with early stopping indicated. Our encoder classifier model demonstrated top 1 and top 5 accuracy of 57.9 and 89.2% over a significantly reduced set of 20 classes, and an autoencoder independently trained over 100 classes. Accuracy is somewhat worse than the CNN model and decreases with class scale, though transfer learning may be useful if an encoder can be extended to generate features for new classes. Thank you.